Okay, well, good morning or good afternoon, as the case may be for everybody. This is Dave Castor with EasyPower, and we're going to be talking a little bit here for the next 45 minutes or so about just the basics of doing power flow calculations in EasyPower. Sometimes it's referred to as load flow calculations. And one of the things that's important to understand is that the power flow calculations that EasyPower does, or any other software, this is different than doing a load calculation or that you would be required to do for equipment design per the NEC or some other standard. So those are really two different things. So we talk about the load. We have to kind of refer to, if we're talking about the actual load that we're going to see if we were to meter it, or the load that we calculate to size our cables and breakers and buses per the National Electrical Code. So if you've done a lot of design work like I've done, you're familiar with the situation where you size your electrical system per the National Electrical Code and you come up with the need for let's say a 1200 amp switchboard, and you tell the local utility you need a 1000 kVA transformer based on your NEC load calcs, and they say, that's great, here's your 500 kVA transformer, because they know that the NEC load calcs are very conservative, and typically the actual loads are never going to reach the level that you calculate by the time you take into account all the various demand factors that you add in code, 125% of continuous loads and that sort of thing. So in power flow, we're looking to try to determine what the actual power flows are going to be, what the actual voltages are going to be for the equipment that's running at whatever actual load they're running at. And so the basic issue with power flow is that if I look at this simple system here on the screen, you'll see I have a source, what I'm calling the sending end, and what I'm calling the receiving end. The basic power flow problem is that for whatever load I have down here, in general, the amount of current drawn by this, or power drawn by this load, is a function of the voltage that it sees where it's connected at the receiving end. So as this voltage changes, the kW or kVA or kVAR demand can change. But the problem is that this voltage depends on the voltage drop between the sending and the receiving end. And that voltage drop depends on the current. But the current depends on the load, which depends on the voltage, which depends on the current. So the only way to solve this is to iterate, or trial and error. But typical solution method is going to involve iteration to narrow down, kind of zoom in on the right solution. And so in the power flow, we're trying to match all the power in with the power out, and all the losses, all the kW and all the kVARs need to balance out. So that's the basic power flow solution we're trying to look at. So in EasyPower, the loads, so basically when you do a power flow calculation, you need to have some realistic idea what the peak load might be. A typical industrial system, if you just take all the load as connected load, run a power flow at 100% connected load, you're going to get generally a very unrealistically high value of load, because not all the equipment is going to be on at the same time, and virtually none of the equipment that's running will be running at 100% of its rated amps, okay, full load. So part of the problem then in doing power flow is coming up with a realistic model for what your actual loads are going to be, and we'll talk about that in a little bit. But the basic concept in EasyPower is you're going to model your system, you're going to put your loads in, and then you need to scale these loads to reflect the reality in your system. So if I go into my motor data here, I have my basic nameplate data for the motor, 100 horsepower, full load amps is whatever it is, power factor and efficiency. That results in a certain kVA that's used. In this case, 98.8 kVA is what EasyPower is going to use for that load, connected load. But now if I go to the power flow tab, there's a scaling factor for every motor. And so this scaling factor is used for the power flow calculation. So the default's 100%. So basically, what this is 100%, I'm using connected load. If I scale this to 80%, EasyPower is going to take the calculated kVA connected, multiply it by 0.8, and that's what it's going to use for the load and the power flow. So it's important to understand that to do the power flow accurately, you're going to have to scale your loads to get a realistic value. Now the load type is used by power flow to determine how the load varies as the system voltage changes, as the voltage at the motor changes. So the default is constant kVA, which is the most conservative generally. So this is saying this motor is going to draw a constant kVA regardless of the voltage at the motor terminals. That's not quite realistic, but it's reasonably useful for kind of worst case simulations. Constant kW and constant reactive current value is maybe slightly more accurate, but at any rate, you have some choices here, and we'll probably do an advanced power flow session here in another month or so, and we can talk about those things then in some more detail. But the default's going to be constant kVA, and that's a reasonable place to start. So anyway, the key thing to remember is each motor has a scaling factor that's used by the power flow module for calculation. So if you look at the specifications tab again, we see a service factor and a demand factor. These things are used for sizing equipment or for an NEC load calc, or if you're doing auto design, it might be used. But these values are not used for the basic power flow calculation. Power flow calculation is going to look at this connected kVA times this scaling factor. Okay. We have the same scaling factor option under our general load category. So this little downward arrow here is just a generic, some type of load, electrical load. If I bring up that data, you'll see I have three different load types: constant kVA, constant current, and constant impedance. So again, as a default, you could enter it as constant kVA. And if it was like so constant Z would be constant impedance. That's a load that, like a resistance heater, something where the load, the resistance, the impedance of the load does not change. And so that's modeled as a constant impedance. And so your kVAR, your kW and kVAR value for that would be at rated voltage, whatever that is, whatever's on the nameplate typically. Now, as long as we're looking at this, for the generic loads, we have these options for how we enter the load, depending on what works for you. The default is, I believe, megawatts and megavars. The vars are the reactive power. So the typical inductive load, the megavar needs to be a positive number. If this was a capacitive load, then this would be a negative value of vars. You can enter it in amps at some power factor, kVA at some power factor, or kW and kVARs, which seems to work a little better for industrial loads for me. MVA at a power factor, and megawatts and megavars. So those are the options for how the load gets entered. And you'll see that it will do the conversion for you. If I change this on the fly, it's going to recompute that for me based on the previous units that I had in there. But I have scaling factors then for each of these load types. And again, this demand factor is not used in the power flow calculation. Okay, So I'm going to take a look at we can do it in this file. So in EasyPower, we have the different analysis focuses. So if I want to do power flow, I have to go to the power flow focus. So that's this selection here. If I select power flow, then my choices up here in the ribbon change. Okay. And so now I see choices and menu options related strictly to power flow. So if you're used to doing short circuit calculations or arc flash, you know that in short circuit I can go in and fault any one bus. I can double click on the bus or whatever select however many buses I want and just fault those buses for my short circuit or arc flash calcs. In power flow, that is not possible. So you have to have a solution for the entire system. It's trying to balance out the VARs and the watts throughout the system. The only way you can do that is to solve the power flow for your entire model. So it's very simple. So we just have one button that says solve. So if I click that, then I get my solution presented to me. Just to talk a little bit about what these numbers mean, let me zoom in a little bit here. So for the branches, whether it's a transformer or conductor or whatever it is, I have these branch flows. Now, depending on, I have some choices in the units. Right now, these are in megawatts and megavars. So the number here without the parentheses, I believe this is power factor, I think, right now. This is the megawatts, and this is going to be the reactive power or the power factor, depending on which units you've chosen. This is a source, so I believe this is power factor. If I go down here, I can tell that because there's no arrow here. If I come down to this is the branch flow. I have 481 kilowatts, 0.481 megawatts, and I have 173 kVARs, 0.173 megavars, flowing into my system. And so the arrow indicates the direction of power flow, the real power, and the VAR flow. So these are basically lagging VARs flowing into my system. If I get down to here, I have similar data at the other end of this cable. So we give you basically the power flow into the line and the power flow out. There's an option to simplify this if you only want to see one end or the other. Kind of clean up your one line a little bit. But basically you see here 461 kW going in and 151 kVARs going in. So if you look at this, you'll see I have more watts and VARs going in than I have coming out. So where did they go? Those are the losses in the cable itself, in this feeder. All right. Down here I have this, where we normally in database we'd be showing the nominal system voltage. This is the actual bus voltage for these power flow conditions in per unit, and this is the phase angle minus 1.6 degrees relative to my source. Okay, my source is always going to take my swing source, or one of the utility sources is going to be referenced as 0 phase angle, and everything else is referenced off of that. Down here I have my loads, so this is going to be megawatts here. I can't remember what units I displayed these in. We'll take a look at the options in a minute. So we'll see that some of the things turn red, and that's an indication of, usually when things turn red in EasyPower, that's not a good thing, although it's good for us today because it's more interesting. This value here is the actual current through this cable. 614.5 amps. The rating of the cable, the ampacity, is 620. So EasyPower is telling me that I'm getting close to the rating of the cable, which is within 0.9%. That's why this turned red. All right. So that's the basic display you get in PowerFlow. Let's take a look at some of the options that we have for the units that get displayed. So when I'm in PowerFlow, I have PowerFlow options, just like in short circuit. I had short circuit options. So now in PowerFlow, I have PowerFlow options. So if I take a look at this, we'll come back and talk about the control in a minute. Let's take a look down here at one line output. So we have selection of how many units, how many decimal places you want to see for the basic and then for the bus voltage. Now, you remember I said we show both the from side and the to side for the branches to the lines. This is an option. If I only want to see one side or the other, I can turn it off so I only see one end or the other of the feeder. Okay, so that's that choice. Now down here is where we have control over the units that get displayed. So the default for the bus voltage is per unit. I can also display that in kV or in volts. So 455 volts here on a 40 volt system, or kV. Okay, so that controls what you see on the one line in terms of the voltage. The branch flows are the flows in the lines or the transformers. So those right now are in megawatts and megavars. So the value in parentheses is always related to the reactive power. This value is the real power. So 0.481 megawatts and 0.173 megavars. I can change that to kW and kVars for the branch flows. I also have display it in power factor. So 510 kVA at 0.941 power factor. Or just current in amps, that's another possibility. Now down here we have the loads, and we have options for those under generation and load. Generation would include the utility sources, not just a local generator. Any source of power is considered generation in PowerFlow speak. So right now this is in MVA and power factor. I could change that to megawatts and megavars just to show you the difference. So you have individual control over the units that get displayed and the losses, which we're not looking at right now, but typically you're going to probably use a lower unit for those kilowatts and kVars unless you have a massive system. So that controls what we see on the screen. The text output, we'll probably talk about that a little later today or when we do our advanced session. There's a whole variety of summary reports that we can generate, and we have a detailed report of the power flows in and out of every branch, every bus, and all the different branch flows in and out. And you have some options here for the voltages and MVA or kVA for the branch flows in the text reports. All right. Oh, let's go back and look at one more thing. You'll see that this bus here turned red, and the reason it turned red is because the voltage is low. It's 0.949 per unit, so a little under 95%. If I go back to my control, you'll see I have a bus under voltage threshold of 0.95 per unit. and an overvoltage threshold of 1.05. So this is saying anytime there's a voltage at 0.95 or lower, the bus is going to turn red, and it's going to flag that for me, that telling me that voltage is low. Likewise, if the voltage goes too high, it's going to flag that. All right. Okay, so those are the basics. Let's go look at a more complicated example to get an idea of what things might look like on a real, semi-real system anyway, and look at some things we can do while we're in PowerFlow and why you might want to run PowerFlow. So I'm going to open up another file we have. We use this in our training classes, so if you've been to one of our classes, this might look familiar. I'm going to zoom out here just so you can see the overall system. So you can see it's a little larger system. And I'm going to zoom back in a little bit here. One of the things that we need to deal with in PowerFlow that we don't have to worry about for short circuit or some of the other analysis, arc flash, are the way that we model the sources in terms of PowerFlow. So when the PowerFlow is running, when the PowerFlow engine is doing its iterations, it's trying to balance out all of these watts and vars in the system. And so it needs a source, at least one source, that it can use to balance out the equation. It's kind of the slush fund for the PowerFlow. And we call that a swing source. And you might hear it referred to as a slack source, some literature. Basically, to run the PowerFlow analysis, we need one source that's modeled as a swing source. Normally, that's going to be your utility source. If you only have one source, then it's a moot point. But if we look at, let me go back to database here real quick. If I look at this utility data, here's my short circuit information like we're used to getting from the utility and entering. But we also have a PowerFlow tab. So if you haven't run PowerFlow, you might not have bothered with this, but this tells the PowerFlow engine how to treat this particular source when it's running the PowerFlow. Okay. So the key thing is how it's modeled. And there's three choices, but normally your utility source is always going to be the swing source. And I have to have at least one swing source to run PowerFlow. If you don't have a swing source and you try to go into PowerFlow, you're going to get an error message. So I can have more than one swing source, but I have to have at least one. Okay. Now, the other issue is the voltage. This is my control kV and per unit. So when I run PowerFlow, that's going to be the voltage that my source is connected to. So whatever I put here, that is going to be the voltage at that bus in the PowerFlow. That's not going to change. That'll be a constant value. So if your utility source typically runs high or low, you can adjust that here and enter whatever your actual utility voltage typically is, okay? Now you may need to create different scenarios to model different PowerFlow conditions. The PowerFlow modeling is the scenario manager is very valuable on that because we have different, usually PowerFlow scenarios we want to model, so we can create different PowerFlow scenarios. But in general, for the swing source, this is going to be, by definition, the voltage that you end up with here. Okay, so just remember you have to have at least one swing source. That's our slush fund for watts and vars. Sometimes it can be negative, sometimes it can be positive, but it has to have a way to balance these out. Okay, so the other typical source you're going to deal with is our generators, synchronous machines. Let's take a look at those real quick. So again, I have my generator data from my specifications tab, but here I have the PowerFlow tab, just like I had for utility source. So I have the same three choices: swing, PV, and PQG, whatever that is. We'll talk about that. So on a typical system where I have a cogen system where I have a generator operating in parallel with the utility, you're normally going to want the utility to be the swing source, and your generator is going to be either PV or PQG. And that's, the reality is pretty much like that, because you're going to rely on the utility to make up whatever the slack is between your loads on your system and what the generator is producing. All right, so for generators, PV stands for constant power, constant voltage. So you can see here that PV's been selected, and so the megawatts are just set here. We just define that it's going to run at 8 megawatts, right? And that's fairly close to reality. If I'm running a power plant, I set the megawatt output by how much fuel I put into the prime mover. Right? It's not an electrical setting. That's a thermodynamic setting, or that's an energy into the system. And I define that's going to be 8 megawatts in this case. The constant voltage part is this voltage here. This is my set point, and it's controlling at this bus, which is probably this bus. So this is saying the generator is going to adjust, automatically adjust its watts, its VARs, its power factor, to maintain this voltage at 13.8. Okay. So we have a min and a max for the megavars. So what happens is it increases its voltage, increase the excitation, the voltage goes up, the VARs that it's exporting go up. If it needs to lower the voltage, it reduces the VARs, and it might even get to the point where it's running at a leading power factor where the VARs are being absorbed by the generator. So it's going to vary the excitation to maintain this voltage, and that we establish a limit here of the VAR range that we're going to allow it to operate in. So the third option is the PQG, and basically there we're just going to set a constant megawatt like we did before. We're also going to set a constant VARs. So this is probably, if you have a small generator in parallel with a big grid, this is a more realistic setting, because in reality you're not going to be able to change the system voltage with your little toy generator compared to what the utility can do. So those are the two main options. One word of caution for the VAR limits here. We said the program iterates, and it's going to go through a range of values before it hopefully converges onto the actual solution. At some point in that iteration process, if it steps through tries to put a VAR value in here that exceeds these limits, it's going to crash. It's not going to crash. It's going to give you an error message saying it can't solve. So if you're having problems with the program diverging, you may want to increase these to some extreme values just to get it to converge, and then come back and maybe fine-tune that a little bit later. So this is a point where you can have issues with the program converging. If it hits one of these limits during the iteration process, you're going to get an error message. Okay, so just remember that I have to have one swing source, and generally you're going to have to make a choice here for the generator. Now, if this, let's say you had a situation where this was a standby generator or emergency generator that did not run in parallel with the utility, and it had a little piece of the system that it powered as a standby system all by itself. So when I run power flow in that situation, it becomes the only source, right? So as I said, I have to have at least one swing source to run power flow. In that situation, you would have to set that generator as a swing source, because I have to have at least one swing source to run power flow. So when it's a standby generator that runs in an isolated fashion, then you'll have to model it as a swing source to run power flow. Okay. All right, so let's cut the chatter and we'll actually run the power flow for this particular system. So I go into power flow, I come over here, and again, I have to solve the entire power model for power flow. I don't have a choice of doing one bus or another bus. So I just click the solve button and there's my solution. So we looked at this briefly before, but again, if you look through here, you can see these values. These are the power flows, megawatts and megabars. See one turned red here. I have my system voltage, my bus voltages rather. So these vary throughout the system, 0.96, 0.966. One thing I didn't mention, in our database, when you define the transformers, you probably recall there's a setting for the tap. So we have the nominal nameplate voltage ratings for the transformer, and we also have a tap setting. So the power flow uses that tap setting to do the power flow calculations. So these values here are the tap settings. Okay. All right. So the thing I wanted to cover was the additional controls we have over the one-line display in the ribbon here. So the things that are in color here are things that are turned on. So I have options. You can kind of hover over these to see what these are controlling. But the first one is the voltage, and that's going to be the actual bus voltage here. So if I uncheck this, turns off all my voltages. Okay. This is the generator data, which is the source data. Turn that on or off. The motor loads, so that's going to be these values here. This just affects the display, not the calculation. Okay, so I can toggle those on or off. The branch flows are going to be these values that we looked at already. So toggle those on or off. Transformer taps, can toggle those on or off. Overloads, that's going to show me, like we saw in that cable where I had an overloaded cable or transformer, and the voltage violations, which we saw, where that shows the low voltage situations. The ones we're not displaying right now are the voltage drop. If I check that, it's going to give me the voltage drop in every branch. Okay. So here across the transformer, which is where most of your voltage drop is going to be, 3.3%. If I look at one of these cables here, it's 0.028%, much lower, but that's the voltage drop I can turn on. The last one is the losses. This gives me system losses, okay, across the branches, the lines in the system. So for my cables and transformers, I get a tabulation of the losses here. I have to caution you that these transformer losses here are the load loss. These are copper losses, I squared R, and that does not include the core losses, which are typically much lower, but these values are just the line losses, the normal losses through the transformer. It does not include the core losses. So that's that display there. Okay, so somewhere down here, oops, turn something off. Okay. So you can see I have, turn my voltage violations back on. You can see I have some things that turned red here. We're going to just talk about those briefly. So we saw in that little model I had before, when the voltages get low, they turn red. So in this case, we see this voltage is 0.939. That's below my 0.95, so that turns red. This is an overloaded cable, so it's telling me that I have a rating of 250 amps, but it's calculating 640 amps, so that seems like a problem. Similar overloaded cable here. And if I come up, I see a similar situation with the transformer being overloaded. Okay. This is the rated amps, and this is the actual calculated amps, and so I'm exceeding the rating by 47%. Okay. So a couple of things to keep in mind is that if you've used the short circuit calcs and used the smart breaker feature, you'll know that you can double click on any particular breaker and it'll open or close and it'll rerun the calculation. The same concept works in PowerFlow. We have the smart breaker in PowerFlow. If I double click on this breaker, it's going to open that breaker and rerun the PowerFlow. So let's do that. So you can see this breaker opened. My load went away here because there's no power flowing, and my voltage went up a little bit. So if I open this one, then my voltage goes up even farther. So that option is always available to you in PowerFlow. Okay. The other things that we can do in PowerFlow while we're in PowerFlow is to change the scaling factors. So if I go to any particular motor, remember this is temporary data because I'm in PowerFlow, I'm not in database. If I change the scaling factor here, well, I'm in PowerFlow. When I go back to database, it's going to ask me if I want to save those changes. So at that point, I can say yes or no. But the scaling factor is 100% here. If I change this to 50% and say OK, it's going to rerun the PowerFlow, and now I'm going to have half of the load here. So the scaling factor, the PowerFlow just multiplies the connected load here by that scaling factor and recomputes the PowerFlow. Now I can do that as a group as well. Instead of having to go back to each individual device, let's say I highlight this group of motors. I have a scaling factor button up here. So if I can press the scaling factor here, I can change anything that I've highlighted. I would be able to change the scaling factor. So I want to change these all to 70%. I can do that. It's going to tell me it's changing 3 items, and it's going to rerun. So that's going to be a kind of a tool you need to use while you're in PowerFlow to scale your loads. So the reality is that to get an accurate PowerFlow, you need some idea what the actual loads are on the system. So ideally, you would have some kind of load data for all their major buses, but as a minimum, you'll want to get whatever the utility service is, get the maximum demand that they've ever experienced. And then ideally, you would scale your load so that when you get up here to the utility interface, that this value would match their peak demand or whatever it is you're trying to model. So then you probably want to store that as some scenario so you could keep coming back to that. So you're going to want to eventually, this is going to need to match whatever the peak demand they've experienced with the utility. Okay. So the scaling factor gets used quite a bit, and so you can come in and select entire substations or motor control centers and scale all those motors up or down as you need to match the load data that you actually have. All right, so let's look at a couple more things here that we can do, kind of what if things while we're in PowerFlow. One of the other options we have is to, if I'm trying to improve my voltage, is I can change my transformer taps, right? So if I double click on this transformer, we have the taps. So if this is, again, temporary data, so if this is a typical transformer, it's going to have some taps on the primary side. And right now it's set at the nominal value of 13.8. And so if I want to increase the voltage on the low side, the 480 volt side, I'm going to go to a lower tap here on the primary. So if I say it's a 2.5% taps, if I take 97.5% of 13.8, I'm going to get about 13.455. So I can just enter that in. I say OK. It's going to rerun the power flow, and then my voltage is going to increase by 2.5% basically. If I do it again, if I go to a even lower voltage, so the full 5%, to get out my calculator here, so 0.95, 13.11, then the voltage comes up, and this, I finally get it above the 0.959. All right. So the transformer taps are something that can be changed on a temporary basis. If you have a generator that's running in your system, you can change those settings. I can increase the megawatts I've scheduled, or the VARs if I'm in PQG, or I can change the voltage set point here as a temporary setting. All right, one other thing that we can do to improve voltage is to add capacitors. Typically, if you add capacitors, your voltage is going to go up in addition to the power factor. So let's just do that real quickly here. To add the capacitor, I actually have to go back to the database. So let's see, it's my capacitor. This is my capacitor symbol. So I'm just going to stick a capacitor on this bus right here. Get that out of the way. And I'm going to make this just for fun. We're going to make it a really big value of 2 megavars at 480, which is that's a monster. I'm going to put a switch in here just to allow me to be able to turn this on or off when I'm in power flow. Okay. Now, if I go back to power flow and rerun this, and you see my voltage got very high, right? Now it's over 1. So while I'm in power flow, I can double click on the capacitor and I can actually change the size. Okay. Again, temporary data. If I change it from 2 to 1 and say OK, then my voltage gets back down a little more to a more reasonable level. So one thing to note about the capacitors is here's my power flow data for the capacitor. So I'm lucky enough to have a perfect capacitor that has no losses. So 0 kW and 0.993 megavars, right? So you can see the result here is I have 1.1 megawatt flowing into this bus, but I have 138 kVars flowing out because of the capacitor. If I double click on this, it's going to open it up, and now I can see my VARs are flowing, again flowing back into the bus. Okay, and my voltage went down. The other thing to note is this is not exactly 1 megavar. And that's because my voltage is slightly below 1. So a capacitor is a capacitor. It's not a megavar machine. So it's only its rated VAR output at its rated voltage. So as the voltage goes up, the megavars increase. As the voltage goes down, megavars decrease. So when I add caps, one of the issues is that they're always there unless I switch them. So I have to be a little bit concerned. In this case, if I have a fixed bank of capacitors that's always on, what's going to happen when I have no load? So I could just basically double click on each one of these breakers to open them up, and I can watch my voltage increase. So this is a little high, but it's still within my 0.105 range that I allotted for. So this is just a good way to check your system voltage when you have no load. Make sure you're not going too high. All right, so those are kind of the basics of the running power flow. So again, while I'm in power flow as temporary data, the things I can change are the scaling factors, right? I can change the transformer taps. I can do open and close breakers. And I have control over the generator, some of the generator values, the generation levels, and also utility source. I can adjust the voltages here. So if I decide I want to see what happens at 1.03 voltage, then I get that, right? So when you have a situation where you get this error message basically saying that the program did not converge, and this is typically, you're going to see this when you have generation and utility source in the same system, because you probably reached a limit there on the generation. So if I go back now to my utility source, if I take it back down to 1, so I can start to increase, but it didn't like that either. So you would have to go in and play with your system here, probably make some adjustments to the generator to verify why that's diverging. So we probably won't talk about it today. We also have the option, the program can also automatically adjust load tap changers for you to maintain a certain voltage. So when you have a combination of utility sources and load tap changers and generators, those things can kind of start to fight each other. So you may run into that divergence problem. So again, one of the things to look at is this. I'm suspicious that this probably is creating a problem for us right now. I would increase this to some much larger value temporarily to see if I can get it to converge. I might change the voltage. I see I'm trying to increase the voltage here to 1.01, but I didn't change the voltage here. So that's another issue that you might get into. So I don't know if we made, so that runs. So 1.01 for both, then it ran. So you have to kind of make some adjustments to your system to match the kind of the real world situation to get this to converge sometimes. Look just real quickly at the text reports. I'm not going to spend a lot of time on this, but we have a variety of summary reports. I just want to run through those quickly here. First thing to note is that just like the short circuit reports, these can all be exported to Word or Excel directly, and it's basically a HTML file. The mismatch report is kind of a log of the iterations that it did, and it shows you where the greatest mismatch was. So eventually it converged. Generator summary report, these are all the power sources in the system. Move this out of the way here. Okay. Then we have the load summary report. This is all the motor loads that you have. And then you have a system summary report, kind of that shows you the balance. So generation and system, this includes the utility sources as well. It's not just local generation. So saying I have 26.65 megawatts generation, I have 26.352 load, and I have 302 kW of losses in the system, real losses, I squared R basically. And here's my VARs. Again, so these need to balance out, right? So the megawatts in, megavars in has to equal what's being used in the system. Transformer tap report tells me for each transformer what tap it's on for this particular case that I'm running. And the line overload report is a little misleading. This is going to list every line, not just the overloaded ones. It's basically a line loading report, I would call it. And so for each line, it's going to give you the rating and the actual load and the percentage of load. And the ones that are overloaded, you get a violation here. And again, the red, the dreaded red. Transformer overload report. Again, this is really a transformer load report. It's going to list every transformer, not just the overloaded one. So the overloaded ones will be red, like this little guy here. So I get the transformer data and the percentage of overloading. I get losses for each one of the branches, it's a separate report. And I get voltage drop if I select that option for each branch in the system. Okay, so that's just a real quick overview of the summary reports. If we come back now and look at, we'll look at the detail report real quickly, just so you can see what that looks like. So basically this is organized by bus. Whoops. So for each bus, I have a branch. I get the branches in and out. This gives me the voltage at the bus, and then the various flows in and out of the bus. So that's the, this gets to be rather, on a big system, this gets to be quite a big report. So it provides some additional detail of the flows in and out of each branch of each bus. Okay. All right, so that's kind of our basic overview of power flow. Again, the key is that this is not looking at NEC load calcs, it's looking at actual power flow system, a realistic scaling of loads and conditions in the system. So if you're interested in dynamic stability, one of the requirements, when you go into dynamic stability, the first thing it does is run a power flow. So you need a realistic power flow model in order to do dynamic stability calculations that are going to be, you know, as accurate as you can make them. So that kind of covers the basics of power flow. As I said, we'll probably do another webinar in next month sometime and do some more advanced topics. We'll talk about multiple swing sources and maybe load tap changers and that sort of thing. So, and the motor starting, impact motor starting that we can do within power flow. So I'll see here what we have for questions real quick. And we have a few. We'll see what we can get through. Question on modeling a 200-ton chiller, 445 kVA. It's just going to be a motor load, and you're going to get the full load amps or the kVA rating for that from the chiller manufacturer. It'll be a non-standard horsepower, so if it's hermetic, so you'll have to just model that as a motor. In this example, how many swings did you have? There was one swing source. You can have more than one swing source, and you can actually specify different power angles between the two swing sources. So we'll probably do an example of that when we cover kind of an advanced session on power flow. Generator, if PV and you hit a megavar limit, does it crash or convert? It will. It doesn't crash. You'll just get an error message that says it couldn't converge. So what I typically do is, in those generators, I would increase the VAR limits to like whatever the max is, 10,000 megavars, I think, plus or minus, and see if I can get it to converge, then at least I can start to narrow in on the situation. Another question, are facilities or utility generation? That's a long question. Let's see. So how you model the generator depends on how it actually operates in the real world. You need at least one swing source. So you can make that the generator. You just have to be aware that what your swing source is and that it's going to if you designate something as a swing source and you need 1,000,000 megavars, it's going to give you 1,000,000 megavars, even though that's not realistic, right? So if you have a complex situation where you have multiple generators, utility sources, you may have to create some different scenarios to model different cases and switch back and forth between PV and PQG and swing. Normally the utility source is the strongest source, the most substantial source should be the swing bus for your power flow, swing source. So then your weaker sources would be, they can be swing, but you would typically, for generators, you're normally going to want to model those as PV if they're large. The smaller generators will be PQG if they're running in parallel. Okay. If you have specific issues with generator modeling, I would just email a question to tech support and we can help you out on that. Another question, is there a way to calculate power factor losses? Well, we can calculate power factor, and we can calculate the VAR losses. If you're looking for calculating the power factor penalty that a particular utility charges, we don't build that into the program because there's 1,000,000 different ways that you're billed for power factor. So you can certainly compute the power factor at any particular point in the system. So we can display this value at the interface as VARs or as power factor. And then as far as power factor savings with power factor correction, from your power factor penalties perspective, as long as the capacitor is on your side of the meter, that's all the utility cares about. You may have some preferences as to where you put them because of other constraints like the harmonics and adjustable frequency drives and nonlinear loads create problems for the capacitors unless they're filtered. You may want to switch the capacitors with the motors and that kind of thing. So in an industrial facility, the location of the caps is more driven by practicality and technical issues rather than economics. The economics are to reduce the power factor penalty, and that is really just making sure it's on your side of the meter. Scaling the kVAR, yeah, there's not really a way to directly do that in EasyPower, scaling the power factor or the kVARs. That would be nice to have a temporary way to scale that, but right now we can scale the overall kVA load, but we can't scale the kVARs or change the power factor as a group or as a scaling factor. Can you choose a portion of the whole model and run a power flow? No. So you could isolate, you could deactivate parts of the system and run it that way, but you cannot, basically the power flow is kind of all or nothing. I cannot run power flow on a part of a energized system. I would have to configure it in a scenario and maybe deactivate part of the system. I could do it that way. The switch is only open when it says open. Yes, the default is that all the switches and breakers are assumed to be closed unless they say open. That closed is the default. Can you use power flow to determine the best no-load tap voltage? Well, it doesn't automatically suggest the tap voltage. You would just have to play around with the available taps. EasyPower doesn't know what the available taps are, for one thing, and then you would just make a selection based on, you have to look at no load versus full load when you're adjusting taps. I mean, that's the problem. So you would have to create a scenario for a light load condition, a scenario for a heavily loaded condition, and then come up with a tap that was kind of the best compromise. It's always going to be a compromise. Current injection is used for power flow. Can you import system models from other software like PSSC? Not directly. If you have a particular existing model that in PSSC you'd like to import into EasyPower, I would contact tech support and they can give you some help on that. solve motor button question on that, we will talk about that. That's kind of a impact motor starting, we call it. And globally scale the loads. You can do that. You would just select as a group all the loads, and you can scale those as a large group. There is power loss by heat. Knowing where this, well, the program is going to calculate the losses in the electric system. So it will show you the losses in the system. And so if I look at this transformer, this is the kW losses. These are the VAR losses. This is where the VARs are being consumed, basically, in the transformers. So as far as what you would do with that information would be really up to you at this point. Okay, so we're a little bit over our time. I want to thank everybody. If there were additional questions that I didn't get to, please email me at david@easypower.com or email tech support. So I appreciate you guys attending the session today, and we'll have another one next week, I think, to talk about motor starting with transient motor starting. So thanks, everybody. Again, email me if you have any additional questions. Talk to you next week.